Okay, so thank you very much for the invitation. It's a great pleasure for me to be talking in this seminar, closing this seminar. So thanks, Pierre, for the organization and all the organizers and all the participants also to stay until this last session. So I will speak about a novel integer linear programming approach for global L0 minimization, which it has nothing to be with graph theory. So let me just move. Not sure if I'm doing this. Okay. So let me just explain what is this about this global L0 minimization problem. So it's about sparse approximation problem. So it's in the topic of a sparse approximation problem. So let me just explain you how does this problem work. So the idea of this is that we are given a linear system, hx equal y, and we are asked to find a solution x, which well, it can be a solution, or we should find an x such that it is a solution of the system, or it is almost a solution. So the misfit error for some norm, it's small enough. And on the other side, we want this x to be as sparse as possible. So that means if we take the L0 norm, it's a pseudo norm, which it's actually just to count the non-zero elements of the vector. We want to be this number as small as possible also. Okay, so we have these competing maybe two goals, and these kind of problems arise in several fields, such for instance as data compression, image recovery, signal processing. For instance, just to give an example, data compression. So imagine that you have to send a signal y, which is maybe too big to send. And what we can do is that we can just agree on some dictionary. It's called the dictionary H. And instead of sending y, I can just give you an x, and with H, you can just recover the signal, the original signal y. And well, what I would like to do is to send an x as small as possible. So to send the least values of x as possible. So in order to optimize the number of information that I'm sending. And so it has some applications in all these fields. And in the last years, I think these kind of problems have been given a lot of attraction, and mainly it's because it has also some impact on machine learning stuff. So I'm not an expert on this field, but I think it's related with just selecting a small subset of features in such a way that those features are enough to explain some data or something, or to find a classifier for some data or something like that. So it has a lot of applications, and these sparse approximation problems can. So you can think of several problems with these two goals. For instance, we can just try to minimize the support of the solution, given that the solution is good enough for the misfit error. Or we can do the opposite. So we can bound the support of the solution to some given value k, and just try to minimize the error with a support not bigger than this value k. Or for instance, we can just mix up these two goals and try to do like a multi-objective function with weights on the misfit error and sparsity of the solution. Okay, so we can think of several combinations for these two types of metrics. So in this work, we will focus on problem 1. Okay, so it will be, so we will want to minimize the support of the solution. So we will try to minimize the number of non-zero components on X, such that the system for that solution is it's good enough. So such that the error on the system is smaller than a given alpha. And usually it is used here for the error, for calculating the misfit error. Usually it's used the Euclidean L2 norm, but sometimes there are some works also which use the norm 1 or maybe the norm infinite. We will work in general with these three norms, so with P in 1 infinity or 2. But we will try to focus in particular with a particular interest in the norm 2, which is actually the most used in the literature. Okay, so this is our problem. So just to give you an outline of the talk, I will give some existing MIP formulations for this problem, and then we will see how these formulations are really not good, not a good method, not a good choice to solve this kind of problem. So with that in mind, we will start a polyhedral study, and with this polyhedral study, we can give a new reformulation for this problem, which is actually an integer programming formulation, and then we will see some computational results on these results. So just to start with the existing MIP formulations, so let me just give you for when we are using the L1 norm and the L infinity norm, and then we will move to the more interesting one, to the Euclidean L2 norm. Okay, so the MIP formulations in the literature are using, of course, variables x to find the solution, and some binary variables b, which will state, so each bj will be 1 only if the x is not 0. Okay, so actually it will be 0 whenever the x is 0, and then we will have also some continuous like auxiliary variables w to calculate the misfit error row of the system. So the formulations are really straightforward, so it's nothing special. So we would like to minimize the support of the solution, so the support is given by the binary variables. Okay, so we are going to minimize the sum of the binary variables, and then we are here binding, of course, the x variables with the b variables. We are using a big M constraint, classical big M constraint. So here M should be a sufficiently big constant. We will talk about a little more about that later. Then here we are just calculating for each row of the system. We are just calculating the error. So W will be a bound for the error on each line of on each row of the system. And then here we can just summing the W's, we can just calculate the L1 norm of the misfit error, and we will ask that norm to be less or equal to alpha. So this is the formulation for when we're using p equal 1. The formulation for p equal infinite, it's really similar. We have the objective function, we have the binding big M constraints, but here we, instead of using 1W for each row, we will use just 1W for all the rows. So this W will be the worst error in the system, and then it's clearly calculating here the infinite norm of the error. So this is the MIP formulation for when p is equal to infinite. If we go to the more interesting case, which is when we want to use the Euclidean L2 norm, we find that we can do it. So the formulation is almost the same as the L1 norm, but we need to add these non-linear constraints to properly calculate the norm 2 of the error. But it's okay because so it's a non-linear constraint, okay, but it's at least it's convex, so we can deal with this kind of things. So these formulations are quite okay, so are straightforward, but there is an issue with these big M constraints. Usually, so we know that big M constraints are usually not nice because many things, because it has usually you get weak relaxations. Usually, if the M is too big, you get like numerical instability. But usually, you can always find an M, or almost always you can think of a value for M such that your model is correct. It makes sense. Well, in this case, it's not that easy because we don't know anything about the data, so we don't know anything about how to bound the values for X. So it's not easy to see how to deal with this with this M value. Okay, so in the literature, what they are usually doing, so they propose this algorithm, and the algorithm says the following. So it says just pick an initial value for M, solve your MIP with that M and get an optimal solution, and then check the solution. If the solution has some value like in the boundaries of this box, okay, so if it has some value like touching one of the boundaries of this box, well, then that means that maybe your optimal solution is not really optimal. So then you should increase at least a little the M and repeat, okay? And the idea is to do this until the optimal solution that you get is not touching any of the bounds, okay, in this box. So this is the algorithm which is proposed in the literature. So we started working with these formulations to see how can we I don't know, how can we improve, at least in some sense, this works. And the first thing that we saw is that actually this algorithm is not really nice because it's not an exact algorithm. So you can easily think of examples in which this algorithm will fail to get an optimal solution. So let me show you just some really simple examples. And here we have, so this is H, this is Y, so this is alpha. We are using the norm 1 to bound the mystery error. And so here what I'm shading here in this rectangle are all the feasible points. So we are in 2 dimensions, so we have x1, x2. So these are all the feasible points. And since we are trying to minimize the support of the solution, so we can check here that the solutions with a minimum support are here in the axis, right? Because so here in this segment, all these solutions have x1 equal to 0. All these solutions have x2 equal to 0, and all the rest of the solutions have a non-zero value for both for x1 and x2. Okay, so these are actually the optimal solutions for this problem. But if we start, for instance, with an M of number 5, so we will bound this. We will use this box. Okay, so this will be our feasible set for the beginning, and we can see that every point here has the same support. So every point here has support 2. So every point here is equally optimal. So if we are maybe unlucky, we will get, I don't know, some guy over here, which is not touching the boundaries of the box. And then the algorithm will stop, will say, okay, I have an optimum solution, an optimal solution, and it's not true, because if we can use a bigger value for M, we will just reach either this or either this, and those are the real optimal solutions. So this is really an example in which the formulation, the algorithm to deal with this big M fails. So one can say, okay, yes, but if you are solving your formulation with simplex or something like that, maybe you will get a vertex of your feasible region, so you won't get in this problem. Well, we can just easily find examples in which that happens also. Okay, so for instance here, these are all the nice guys, all the feasible guys. These are the optimal solutions. And by using this M, we can see that we will have this feasible set. okay, which is all equally optimally. And then if we are not lucky, we will get this guy over here, and we will say, okay, stop, and that's not good, right? Because we wanted to reach an optimum, which are lying here, okay. Also, if we move to the more interesting case, which is when using the norm 2 to bound the misfit error, we will easily find the same kind of problems. Okay, so in this case, we have the same kind of problems. So let me just move on. So the question here is, okay, but can we do something to find a proper M? I mean, maybe we can do something like a pre-process to find a big M which contains all the feasible set. Maybe, I don't know, maybe solving, just maximizing each coordinate separately and trying to find like a big box containing all these feasible guys. Well, then the answer is no. We have some examples. For instance, this example, the feasible region is unbound. So the feasible region is it goes on like on this direction. So we cannot bound the feasible region with a big M. Okay, so this is a problem. So these formulations have had this problem that it's not clear how to deal with the big M approach. Just an observation, we can get rid of the big M constraints, so it's not strictly necessary. For instance, we can add this non-linear equation, which would be like the same as the big M constraint, but this is really ugly because it's non-convex, and it really complicates the resolution of the thing. So we want to stick in the, at least in the convex thing. Okay, so so just to sum up up to now, so in order to remove this big M, we will get some non-convexities, which is not nice. If we keep the big M, then it's not clear which M to use or how to obtain it. And then another thing, even if we, for some reason, we know something beforehand, and we know some bound for X, well, then we still have a big M, the known big M issues, because it's a big M formulation. So in any case, the solution so far is not quite elegant. So our goal here was, okay, so we find out this. So our goal was at least to study this problem and study this formulation, these polytopes, to try to do something with it. So we started this polyhedral study. Just let me give you some definition, which will be really used in all the presentations. So the forbidden support. So we use that. We say that a set of columns J, we call a set of columns J to be a forbidden support for this problem if there is no solution with that support. Okay, so if we pick some columns and we can check that there are no solution just restricted to those columns, then we will call this set of columns to be a forbidden support. So our first result was a really simple valid inequality for these polytopes that says the following. So if you have a forbidden support J, then at least one of the columns outside this set should be selected for the solution, which is really trivial. It's really straightforward. So if J is a forbidden support, that means that if I restrict myself to J, I cannot get a feasible solution. Well, then, so at least one of the columns outside this set should be selected. Okay, so this is true, right? So it's a valid inequality for these formulations. It's not clear how to deal with the separation procedure for this, but we will speak about that a little later. Just a few nice things about forbidden supports is that we can test really efficiently if a set of columns is a forbidden support or not. Okay, so actually, if we are in the cases of P of the norms 1 and norm infinite, we can just solve an LP, minimizing this guy, and that will tell us if it is a forbidden support or not. So we just find this minimum and compare it with alpha. Okay, so this can be done with an LP. And the more interesting case, and actually is the case in which we are more interested to solve, is when we are using the Euclidean norm, the norm 2, is that we can do this not by solving an LP, but just solving a least square problem. So it's a really fast way to check if a set of columns is a forbidden support or not. Okay, so this is a really nice point about the forbidden support inequalities, or about forbidden supports. So now let me tell you, so we keep on going with these families of valid inequalities, and we found a really interesting thing, which is related to the following. So at first, so we have our formulation, so the formulation, the original formulation. So assume this is a really bad sketch of the feasible solutions. Assume that these are all the feasible solutions for our formulation. We have some, so we have the x values, and we have the binary values here. And let's do the following. So let's suppose that we project here, so we project all the solutions on the binary plane. Okay, so on the plane of the binary variables. Okay, what we can do, so here we will call this P proj. So the projection of here is actually all the binary vectors such that there exists at least one solution X associated with that vector. Okay, so this is kind of the set of all feasible support for our problem. Okay, so one more thing about this is that we can, this is really based on the other proposition that I told you before, but there is a nice thing about that, is that if you give me one guy here, so if you give me a feasible support, then I can easily, very efficiently lift that point to obtain a proper solution X. Okay, and when I mean efficiently, I mean either by solving an LP if I'm using the norm 1 or infinite, or by solving a least square problems if I'm in the case of using the Euclidean norm. Okay, so these states are really interesting thing, because since we are trying to minimize the sum of the B variables, actually what we can do here is just to forget about the X variables and just work here. Okay, so we just optimize our objective function here on the projection. So on the set of all feasible supports, we don't care now about the X. We minimize the support in the set of feasible supports. And then at the end, when we find the minimum support, we just need to lift that solution B to obtain a proper solution X, and that is our solution for the problem. So this is quite nice, but of course the thing is that, okay, but we don't have a proper characterization of this, because the only characterization we have until now is that, okay, so these are all the feasible supports, and that is not nice. But here it comes the interesting remark about forbidden support inequalities. We could prove that actually these guys, so the projection, so the set of these supports for our problem is completely described by the forbidden support inequalities. Okay, so we can just forget about the X variables and use just the forbidden support inequalities, and that will give us a description for these guys over here. Okay, so what can we do? So this is the new IP formulation which we are proposing. So the idea is, okay, so forget about the X variables and just minimize the binary variable, so minimize the number of non-zero components, such that your solution satisfies all the forbidden support inequalities. Okay, so this is now the formulation that we will use to optimize here. And then finally, when you get an optimal support, you just need to lift that support efficiently. I mean, solving a least square problem, for instance, and that's it. So this is the reformulation that we are proposing, and it has some interesting points. So it's a linear formulation. Actually it's a pure integer program, even for L2. So even if you are dealing with the nonlinear norm 2, you get this linear formulation. And the best thing is that this doesn't need to use a big M. So we don't need a big M here. We just need these constraints, and we are done. Okay, so that is really interesting. Another interesting thing is that this is a set covering problem. So we can see that it's actually a set covering format, right? So it's a set covering formulation, I mean. And so this is really interesting because we know a lot about set covering formulations. So we know that they are nice, they have nice relaxations and so, but also we have a lot of heavy weaponry to attack this kind of problems usually. So there's a lot of work done on this kind of formulation. So this is something that we should exploit in the future, maybe. On the other side, of course, it's a bad point that it has exponentially many constraints. So all these forbidden support inequalities. So we don't have it at first. We don't have it at hand. We cannot write them all. So we have exponentially many constraints. But this is not scary. So this is something that we are used to handle. So we can just do something to deal with these exponentially many constraints of the formulation. So for instance, we propose, well, somehow it's a really straightforward approach. So instead of solving the full formulation, we will just solve a combinatorial relaxation of the formulation, dropping a lot of constraints and just starting with a bunch of these guys. Okay, or actually in the implementation we start with no constraints, and from there we start to add constraints. So start with a combinatorial relaxation with maybe just say a few constraints, get a minimum support for that relaxation, and then we can check. So if the support we got is actually a forbidden support, then we have in hand, so if B is a forbidden support, then B gives us one of these inequalities, okay, to add to the formulation. So we don't have to do anything else. So we just check if the solution is a forbidden support, then with the solution we can add a new constraint to the formulation. And if not, if in case B is not a forbidden support, then that means that B is a feasible support. And so we finish the algorithm just by lifting B and getting a solution associated to that optimal minimum support. So it would be an optimal solution for the problem. Okay, so okay, so I have this funny drawing. So to illustrate the thing, so we want to find a minimum support here on the gray area. We will start just by these three constraints, for instance, and we will optimize. Maybe probably we are minimizing B, so probably we'll get some solution around here. Since this solution around here is not a feasible support, we will add a new constraint to the formulation and keep going. Maybe then we can find something here which is not a feasible support, so we can add the corresponding forbidden support inequality. Then we go on, maybe we are finding someone there which is again not a feasible support, we just cut it, and at the end we will find we will find a feasible support, and we just need to solve this least square problem or LP to get the proper X. Okay, so so this is the new formulation and the proposed the algorithm to tackle this formulation with its exponentially many constraints. Let me just, before going on to see some computational results, just talk about some more polyhedral stuff. One interesting remark about this is that so we have our MIP, original MIP, we have our projection, which is our new formulation, IP formulation, and as we saw, this is actually a set covering formulation. So this is a set covering polytope, and we have a lot of things that we already know about set covering. So for instance, we know many valid inequalities, many families of valid inequalities for set covering polytope. We have many facet generating procedures for set covering polytopes. And since this is the projection of this guy, any valid inequality for this polytope is valid inequality for this guy. So this means that even if we want to stick with the original MIP, we can use a lot of things from the set covering area to improve the resolution techniques for the original MIP. So this is some interesting stuff. For instance, this is an example. I think I will skip it, but this is an example of a valid inequality coming from set covering, which here I just translated this to the forbidden supports world. But when you see this, is something that for me at least, it does not make any sense in the forbidden support world. But we know that this is a valid inequality because it comes from the set covering field, and we can use it for free in a branch and cut approach or whatever. I won't get into the details. So let me just make a quick checkpoint here on what we have. So we started working on these problems, on these sparse approximation problems. We found these big N formulations, and we found these not nice issues about the big N formulations. So they were not considered. So we couldn't consider to be exact approaches for these formulations because actually they were not exact approaches. So we started the polyhedral study. We got this new family of valid inequalities, which are the forbidden support inequalities. And with these inequalities, we could see that they were enough to describe the set of feasible supports. And so with that information, we just we proposed this new IP approach, which by the way is the first IP approach for this problem to our knowledge. And additionally, we could see that actually this is a set covering polytope, so we have many things to profit from in order to add for to improve the solution of these things. Okay, so maybe here is a good point to ask if there is any question. If not,
I have a question, but I can wait the hand. But what is the perhaps I missed something? But what is the complexity of your algorithm to check to find a minimum forbidden set B? Here, this one.
Here, okay.
How many iteration?
Yeah. So the complexity of each step is here. We need to solve an IP. So, well, actually, this algorithm, it's actually implemented in like in Cplex framework using lazy constraints. So it's not quite that whenever you add a constraint, you need to restart everything. So it's actually you go on. But so this actually is just solving a MIP with lazy constraints. And the step 2 and 3 separately has the complexity of these steps it depends on if you are on the Euclidean norm, so if you are using the Euclidean norm or the norm 1 or infinite, but it's polynomial. I mean, it's if you are using the norm 1 or norm infinite, it's to solve an LP here. And if not, which is the more interesting case, which is the norm 2, is to solve a least square problem. So it's just to solve a linear system. So in that case, it's really fast. These steps are fast.
But
Maybe you were
the number of iteration of
okay. So you about the number of iterations, I have no clue. I really don't know because it depends. No, I have no clue, but I mean it's an analog of what we do, for instance, with vehicle routing, right? To break the subtour inequalities, right? So how many subtour inequalities should you get in the worst case? I'm not sure if there are some complexity result on that, but
there is some, but
okay,
not in
good.
this framework. I'm pretty.
Okay.
It is not the same framework now. So
Okay.
for me, this number of iteration can be exponential.
Yes.
Because it's quasi an enumeration in sort of, but perhaps I missed something. So if it's working, perhaps I'm wrong. But.
Yeah. So the results are good. So the results are nice at the end. So, but I really don't have a clue on some theoretical complexity of the number of constraints that needed to be added here. No. But the results are quite nice. So we will evaluate now three approaches. So the first is the original from the literature MIP approach with the iterative algorithm to solve the big M, to try to solve the big M issues. The second one is the same, but by solving the MIP with some simple branch and cut by using the forbidden support inequalities, but as cuts, as user cuts. Okay, so and just some initial rounding. No, sorry, not initial, and some rounding heuristic, primal heuristic. And the third one is the new IP formulation that we are proposing. So just I will get really quick about the explanation of this the branch and cut. So we will use forbidden support inequalities as cuts and some greedy rounding heuristic to find feasible solutions. About the separation problem for the forbidden support inequalities, it is not clear if we can solve this. Just use heuristic separation. It's quite simple heuristic, so I won't go into details. But the nice, interesting thing is that we need to cut a solution, fractional solution for the MIP. But actually, we are not using the X variables, nor the W, so we are just using the B variables. So these same cuts can be applied also for the IP approach, okay? And also the same happened with the rounding heuristic. So at the end, the three approaches are the original one, the branch and cut, which is the original one, but solving the MIP with these user cuts and these rounding heuristics, and the novel IP formulation with the dynamically added constraints, and also with the elements of the branch and cut to solve the IP, okay? And we have two goals here because, so remember that we are comparing actually an exact approach, which is this one, with two approaches that we know that they are not exact approach. So we will have two goals here. We will compare the solution times on one side. For that, we will use real data from this paper. And then we will try to check how bad can how bad can perform these two guys. So actually this guy. about this big M issue that we know that cannot be considered an exact approach. Okay, so and for that we are using some pathological case for these problems, which are stated in this paper. They just build instances which are really difficult to solve for these problems. So we just extract some random submatrices from this pathological case, and so we have these two approaches that we want to check. So for the first one, let's just stick with the norm 2, which is the more interesting one. And so we can see here, sorry. So here we have for each line of the table correspond to a group of instances with some characteristic. This is the signal to noise ratio of the convolution instance. I'm not sure what does this mean, but it's something about signal processing and how much noise the instances have. And this value of k is how they build this data. And actually, what this k says is that we know that there is a solution with support 5. So with just 5 non-zero elements, and with this 7 and 9. So this k is a known solution for that instance. Remember that we are trying to minimize the support. And so for each of these methods, what we are showing here is, well, here's the number of instances for each group. And we are showing how many instances the method solves, in which average time is using to solve all those instances, and then how many instances it did not solve in a time limit. I guess it was half an hour or something like that. And for those instances which are not solved, which is the best solution achieved by the method. Okay, and here we can see that actually our new proposed method is way better in terms of speed, at least. So it usually solve much more instances. We can check here, for instance, it solved all the instances in these two groups, while all these guys solve not all, and sometimes really few instances. And we can check the times also. This, for instance, in this group, it's really shocking that we are, for instance, solving 50 instances in an average time of 22 seconds. And this guy is solving just 12 instances in more than 100 seconds in average. So when we check these values, we can see that this method is really outperforming the original formulations. If we forget about the IP, just to check if the branch and cut is getting better results than just the MIP. Well, we can see that yes, it's not like outperforming like a huge improvement, but it is working better. So the branch and cut is, so the cutting planes are helping in the resolution. So these are for when we are using the Euclidean norm, which is actually the cases that we are most interested in. When we go to the infinitive norm or the norm 1, we don't get nice results. This is understandable because we are solving a lot of times this test to check if a set is a forbidden support or not. And well, in this case, we need to solve a lot of LPs, and in the case of the norm 2, we need to just solve a lot of least square problems. So when we go to the norm infinite and norm 1, the results are not the best. So usually we solve almost the same number of instances, but the time is a little worse. But we need to have in mind, of course, that we are comparing an exact approach with an heuristic approach. So it's not clear how to compare these cases. Okay, so let me just go to the second set of instances. These are submatrices of this pathological case, and here the idea is to compare not the times, but to compare how bad are the other methods performing. So here we have again, each line is it corresponds to 10 instances of this size, and the k is the same. So we know that, so we construct the instance such that there is one solution of this size, okay, with the support of that size. And so what we can, well, and then for each method, what we are showing here is, the first column is the number of time limits. This was half an hour of execution, the number of time limits for that group of instances. Then there is the average support obtained for that group of instances. And just forget the top and best. This means in how many instances the method achieves the best solution over the three and that kind of stuff. But let's just stick with the support. So the idea here is to compare the quality of the solution, which is actually the support obtained. We can see that our method finds supports really much smaller than the other two methods. And one interesting thing here is that we can see that this is not about time limits. So it's not about that this method couldn't find a proper solution because it was slow or something, because we can check here for that for the 10 instances. For the 10 instances in this group, this method, for instance, it didn't went into a time limit for any of those instances. So this means that the method stopped saying, okay, I finished, this is the solution I achieved. And we can see that it's 4 times, that the solution achieved is 4 times the optimal solution achieved by our method. So, and that is repeated in most parts of the table. So this shows really that how bad can these guys perform because of the big M issue that is not an exact approach. Okay, so just I think this final table. Here I am listing all the 40 cases that were solved by the 3 methods. Okay, that I mean solved. I mean that it was not a time limit, so that the 3 methods finished normally. Okay. Well, of course, we know that ours is an exact method, so if it finished without a time limit, then this is the optimal solution. Okay, and then here we can find the solutions obtained by the other 2 methods, and we can see that actually the error incurred is really, sometimes it's really high. See, here I highlighted an instance where the optimal solution was 4 and the MIP ended without a time limit with a solution of 40. So it's really, and this is a solution of 40 columns selected out of 60 columns. So it's really bad. Okay, these instances are like a pathological case. So it's clearly instances that in which these problems are really hard. But well, this evidences how inexact are the methods that were all in the literature. Okay, so okay, so just to sum up, and I think I will finish in 1 minute. Just to sum up, so the previous MILP approaches were not exact, couldn't be considered exact approaches because of the big M issues. What we are presenting here is around this polyhedral study of these approaches, we just reformulated into pure integer linear programs, which are exact, and so to the best of our knowledge, is the first ILP for these problems. And we showed some interesting results, at least in the Euclidean norm, which is actually the most used norm to measure these kind of things. So what's next? I would really like to exploit the set covering structure. I think there is a lot of work in the literature about set covering that we can implement to improve this method. For instance, implement some more user cuts for the formulations, or even profit from non-Halogen heuristics to get some, I don't know, rounding heuristics or whatever. So there is a lot of things to exploit there. So, well, I think that's it. Thanks for your attention. Thanks for staying until now. And if there is any question, I'm here.